Hello, welcome back to Bytes of CEC. So, in this lecture, we'll be learning about the selection sort algorithm. So, in this lecture, I'll tell you what a selection sort is, then I'll make you go through an example to explain how a selection sort algorithm works, and I will take you through a walkthrough of the algorithm, and finally, I'll discuss the runtime complexity. So let's get started. So when we talk about selection, when we say selection sort, so selection means we need to select something. So what do we select? Suppose we have an array A with n number of unsorted elements. So the first step will involve finding the smallest or highest element in the array and exchange that with the element in position 1. In the next step, we will be selecting the second smallest or highest element in the array and exchange that with the element in position 2. And it goes on like this, and at the n minus 1th step, we will be selecting the n minus 1th smallest or highest element in the array and exchange that with the element in position n minus 1. Now, what about the nth element? Now, in an array with n minus 1 elements are in sorted position, so definitely the nth element will also be at the nth smallest or the highest element will also be at the position n. So, if I need to give you a more general overview, so I can say that at any step I, select the I smallest or highest element in the array and exchange that with the element in position number I. Now, in this case, I have considered that the indexing starts from 1. But as I take you through this example, I will be considering that the indexing starts from 0 as per our major programming languages like C, C++, Java, Python, since they all consider that indexing starts from 0. So that was just to make you understand that, okay, at the ith step, I'm supposed to find the ith smallest or highest element and exchange that with position I in the array. So if you are starting from 0 indexing, so definitely you will be exchanging that with I minus 1st element. Okay, that's all. Now this is an array. So these are the elements 14, 8, 90, 2, 7, 5 and so on. And this is the indexing of the array. So I am going to sort this in an ascending order. So that is from smallest to highest. So naturally, in the first iteration or first pass, first step, whatever you call it, you will be selecting the smallest element in this array and you will have to exchange that with the element at position number 1 or with index number 0, that is 14. So in this case, as I go through 14, 8, 90, 2, 7, 5, 61 and 10. So 2 is the smallest element in this array and I will be exchanging 14 with 2. So 14 comes here and 2 comes there. So this is what you get. Now in this second pass, you will have to select the second smallest element in the array. So as you go through this array, the second smallest element is this and you will have to exchange that with the element at second position or element with index number 2 minus 1, that is 8. So this is how it looks. Now before we proceed to the third pass, one interesting thing that you might notice is, say we consider, now in the third pass we will have to select the third smallest element and we will have to exchange that with the element in position number 3 or the index number 2. But before proceeding to that or before viewing it from that perspective, let us consider this entire array. Now, whatever be it, we are not doing anything with these positions. Like 2 is already in its position, 5 is already in its position. So, if we consider the whole array A, So we might form a partition where this is the sorted part of the array and this is the unsorted part of the array. Now in unsorted part of the array, so this is position number 1, right? And as you might say that in the third pass we had to exchange the element, the third smallest element with position number 3. So in this unsorted in this unsorted array, so this is the position number 3 is always the first position, and the third smallest element in the entire array is actually the smallest element in this unsorted part of the array, because we already have the smallest element, the second smallest element, and the third smallest element belongs somewhere in these positions. And if we consider that this part of the array is already sorted, we are not considering this part. If we consider this part of the array, so this is going to be the smallest element of this part of the array. And in this unsorted part of the array, we are actually going to exchange the smallest element with the first position. So if we take that approach, among 90, 14, 7, 8, 61 and 10, so this is the smallest element in this part of the array, and we will be exchanging position with 90. Like 7 will come here and 90 goes here in the third pass. Now again, for the fourth pass, now this becomes the sorted part of the array. This is the smallest, second smallest, third smallest. These are already sorted. So now we are looking for the fourth smallest, or again, if we consider the partition, we will be considering the smallest element in this unsorted partition, and we will be exchanging position with 14, or the first element in this unsorted part. So in this part of the array, 8 is the smallest element, and we will be exchanging position with 14. Again, for this part, this is the smallest element, and it looks like this. For this part, now even though this is already sorted, but we will need to make comparisons in the original algorithm to actually ensure that this is indeed the smallest element of the array. So now positions will not exchange, but this is the final pass where n-1 elements are already sorted. So naturally, this will contain the nth smallest element, or the highest element in this case, in the array. Now let's move forward to the algorithm implementation. Now this is the algorithm. I'm not doing any program, but this is the algorithm. So now, as you have gone through this example, so first we need to keep an account of which position to actually exchange your smallest or highest element with. Since this was in this example, we have arranged it in ascending order. So this also, the selection sort algorithm written over here also arranges elements in ascending order. So number 1, we need to keep a tab on which position to exchange, like at pass 1 we have to point to the 0th element, at pass 2 we have to point to the index number 1, and so on. So for that we need one variable, and also we need to find out the smallest element among the unsorted part of the array, and for that we need to consider a loop which will make comparisons to find that which is the smallest element. And again, we need another constant variable which will keep an account of which index is so far contains the smallest element. So at the start of the array, what we do is we consider that the first element itself is of the unsorted array, of course. The first element itself contains the smallest element. Now we will be, so in this case, as you can see, for I in range 0 to n minus 2, that is for I equals to 1, I less than n minus 2, less than equals to n minus 2, I plus plus, which will be the C equivalent of this step. So we consider that now this temp is actually the variable that will consider the index, that will contain the index of the smallest or the highest element. So we initialize temp to I. Now we start the J loop. Now J loop will start from the position immediately to the right of I, that is from position I plus 1, and it will go on till the end of the array. Now since the indexing starts from 0, so this is going to be the n minus 1 position. Now we will consider that if Aj, that is the element contained in position J, is less than a temp. If it is so, we will be, temp will be getting the index number J. Say for example, let us start from the first pass. So here the temp, this is the value of the temp. So temp is 14, this T is for temp. So temp is equals to 0. Now we start the loop from J, which is position number this, that is position number 1, 0 plus 1, okay. So now we consider that if AT or A temp, that is 14, is less than 8. Sorry, AJ is less than 8 temp, sorry. If AJ, which is 8, is less than 14, yes, it is less than 14. Now temp gets the value of 1. In the next iteration, we will be considering that if now your I is maintained at here, only the temp position has changed, because I has to be here, because here is where the exchange is supposed to happen. So now temp contains the value 1. Now if 90 is less than 8, no, so temp stays at 8. Next we move on to this, that is the position of J is now 3. Now if A3, that is 2, is less than 8, yes, 2 is less than 8. Now temp is now temp gets the value of 3. Okay. Now we will be considering if 7 is less than 2, no. 5 is less than 2, no. 61 is less than 2, no. 10 is less than 2, no. So the value of the temp after the end of this J loop is 3. Now we will be exchanging the value contained in position, index number 3 with the value of position, index number I. So I is initialized at 0 in this case. So 14 and 2 gets exchanged in this pass. Now in this pass, see, I moves to the second value, that is now I is here. This is I. This is not considered. So now the same thing is repeated. Temp is again initialized with temp is again initialized with value of temp to be 1. And now again comparisons are made and the algorithm is repeated like this. And finally we get the version of the sorted array. Now much can be said about the runtime complexity of this algorithm, but I am trying to explain it in a very plain and simple way. So see, in the first pass, consider there are n elements. So in the first pass, the number of comparisons made is n minus 1. Yeah. In the next pass, the number of comparisons made is n minus 2. In the third pass, number of comparisons are made, that is n minus 3. Up till, so this continues, and finally we just need to make one comparison. So if you can if you just go through this entire this summation, this is like an AP series where the sum of this AP will be n into n minus 1 divided by 2. So these many comparisons are made in total to actually find the sorted version of this array. So as you can see, this you can always write like n square minus 1 divided by 2. And since we do not consider the constants when we are trying to express that in asymptotic notation, we will be saying that the runtime complexity of this algorithm is of order n square. So O(n) square is the runtime complexity of the selection sort. Now, if you want a more detailed explanation of this runtime algorithm, this was a very, what shall I say, a simplified explanation. If you want a detailed explanation, I can make a separate video on that. I don't want to make this video too long. So that's all for today. Thank you for watching.